Hello everyone, welcome back. So let's start where we left off yesterday, and it's this exactly. So previously we had the allocate memory that's just going to use a bitmap to keep track of pages, and it's gonna give us in bit index of new pages that are currently allocated in array. After that, we have the high level helper that's we are gonna call it as Kernel, and it's gonna take the same bitmap array bitmap the pointer to it and the size that we want to allocate, and we are gonna write this call this helper that's the previous allocated mem, and it's going to give the total number of pages that are allocated, and the result array will have the indexes of the allocated pages. Now we can use just the first, and that is the top of the because assuming those pages are in a series, so like 17, 18, 19 are there like contiguous blocks. So we could just take the top of the first page, and we use the index to calculate the physical address, because the indices into the page size would give the actual PA, that's the physical address, and we could just add FFFs in the front to convert it into a VA, because we only have identity mapping. So in our case this should definitely work. And now we are supposed to write this helper that's going to take virtual address, and it's going to add page table entries, because that's the key. Because right now we have even if we can we even if we logically say that we have allocated these pages, if we try to access this memory, we would just get a memory page fault, because there's no entries for it. And finally we could just return it as white star. That's it. And now we can start writing the function. We really don't need much information about it. We could write it ourselves, and it should be page table entry, and it's going to take a VA that will be u in 64 value. Oh, fuck. U in 64T, there's the VA, and we also need the total size. That will also be u in 64 value. That will be the total, and we could, I don't like this structure. Okay, this looks better. Okay, now what do we do? We have to return false if we reach the end. And okay, now let's think about the certain things that we have to actually know to implement this. That would be, this will be called from kernel alone. So if it's always called from kernel, we only have to update the kernel tables. Update kernel page table. So what's the registry for it? What's the registry? I guess we just go back to our MMU unit. We should be able to find it. I think we are using We are using virtual address here, so yes, it should be there. Yes, we are mapping the kernel virtual address, so yes, it should be there, and we are mapping it to, I suppose it's this TLBR1 because it's EL1. I guess we are setting both the tables to the same thing, so even from user level we should be able to access it, but this is not bad. Let's add a to do. Fix this user space should not have access to this page table entries. Okay, and yeah, this should be the one. Let's copy that. Was our function that we were writing? It's below kmalloc. Okay, and it's just this. We have to update this. We have to update this entry, and this entry is like it can either have a block entry, block value, or no, it can have a table descriptor or block descriptor. Yeah, have a table descriptor or block descriptor. I don't know if I'm spelling it correctly. Well, whatever. So you can have either a table descriptor or block descriptor. Now we could also give the user the variable, like maybe we can add another thing that will be the flags, so he can actually change it. Yeah, let's start with hard coding it, and then we can think about improving it. Let's just get something working first of all. So let's take an example and go through it manually, and then we should be able to write it. Let's say we want to allocate memory for this 1 2 3 4 1 2 3 4 1 2 3 4 1 1 2 3. We want to allocate memory for this, and this has to go to this entry 1 2 3 1 2 no 1 2 3 4 1 2 3 4 and 1 2 3 4 1 1 2 3. Okay, this is what we have to write, and this will be the inputs, and let's assume that the total is just 1, so we have only allocated one page table, so that's the input. Now what do we do? Now we have to create a so let's just always create a block descriptor. That way we'll have the initial table entry, and within the table entry we find the level 2 table. So there's 3 levels, so let's consider I guess we could Google it. It would be easier to visualize it. Page table entries in I guess this should give, yep, this is the one. Not sure if this is the one. Translation page tables, translation table walks. table walk developer. Oh fuck me. Table walk reference. That was a PDF I used previously. It was really good. Yep, something like this. Do we have this PDF somewhere? Why the fuck he didn't just... Oh, this is some sort of MD format. Maybe this is actually getting converted to PDF. Well, whatever, let's just use this information to keep going. So this is what we have to, we are going to be caring about. Why is it here? Okay, no, okay. Now let's, as you can see, I guess if you had looked into my previous, I guess it's in the third part where I explained how table walks work, and based on the address range we select, that is the VA bits, will have different levels of tables. So if we select 48-bit VA, that would mean that the virtual space is of first 48 bits. So this is like the 64-bit total. So the first 48 bits will be given to the actual addresses, and the rest will not be used as an address. This is just for figuring out if whether it is a kernel user space address or is a kernel space address. That is the EL0 or EL1. That's the only difference that this is gonna give, and that's exactly why we need this difference, and we provide the value. So how much memory should I have in a user space, and how much memory should I have in the virtual space, no, in the kernel space. And in my example, I have considered as a VA, 48-bit VA. In my example, it's a 48-bit VA, and you could see it here. If we come back to our main example, the MMU, yes, as you can see, we are setting the TCR. This register should be the actual that is holding this information, and the first I guess this bit is going to say what is your page size, and it's 4KB, and 16, this is gonna set my this particular field to 48-bit VA, but it will be registered as 16 because it's 64 bits. That's the total minus 48. That's why we register it as 16, but it actually means it is 48-bit VA. And I guess the rest is for TL1. Okay, so this is for the kernel and this is for the user space, because this is T01, because T01 means EL1, T00 means it's EL0. But we only have to recall this one fact that VA bits matter. Based on the VA bits, we'll have different levels of tables. In a 48-bit VA, yes, if you consider this, we have four levels of tables, and the first, if we say the first level can never be a block descriptor, it's always going to be a table descriptor. So the first level is going to, every index within this level, it's going to be like 256 TB. So let's say I want to allocate an table for this, no, allocate entry within the table for this address. then we have to first figure out on which table this will fall under. And it's probably going to be within the first 158 GB. So because this is not higher than 150 512. uh, yeah, it's definitely not higher than 256 dB. So the first entry will be 0. The second in the within the second index, we have to think about the bits 38 to 30. I don't think we have those bits, so the second table will also be 0. And the third index will be considering 29 to 21. I guess even here that is still 0. This, I guess, 29 to 30, 21. I guess the here I guess will be still be considering it as 0. And the final thing, that is the 12 to 20, I guess this bits will be the one that will be considered here. And in this case probably will be in the first index, because this is the first index last value. I suppose if we had it like something like this, then probably would have gone to index 1. And if we had something like this, and we would have gotten into some other index in this table, and probably some index within this table. So mostly it's just about calculating the index values and properly walking the table and setting the bits. That's what we have to do, and we have already done it properly for our MMU unit. So mostly we just have to copy paste things. Maybe I'll just give you an example. Here we want to allocate a table entry for FFFF 0G8. This is our virtual kernel base. So we need an entry for this. And so we have 3 tables here: the level 0, level 1, and level 2. And within, we don't even get into level 3 table. We only have 3 tables here. And for the now we have to calculate the index for first table. So how do we calculate index for first table? Let's go here. We just move the VA to 39, because we only care about 47 to 39. So what we do is that we right shift it. So let's say we have what does right shift do? Right shift will bring the bits to the rightmost value. So if it was like 0 1 0 0, and if we right shift it once, then it will be like 0 0 1 0 0. And if we again right shift it, it will be like 0 0 0 1 0. And if we again right shift it, it will be like 0 0 0 and 0 1. So this is exactly what we have to do, because in the 0th index we only have to care about 47 to 39. So what we do is that we shift it 39 times. So we will what the fuck am I doing here? It's VA, and is it right shift or left shift? Sometimes I'm fucking forgetting what is right shift and what is left shift. Yeah, this is definitely right shift, because left shift means it has to go from here to here. So this is right shift, and I'm right shifting 39 times. Why am I right shifting it 39 times? So I guess the 39th bit will come to our leftmost value. Let's say the 39th bit is somewhere here it will come to our leftmost value. So we'll only have 39 to 47 from the left to right, and then we can just AND it to only get the final bits, because this will be the actual index. And how did I come up with this number? I guess this number just means 8, I guess. 47, 46, no, 39, 30, 40, and then there's 6. So it's like 8, it's 9 bits. To get the last 9 bits, we are adding this operation, because if we AND it with this, we'll only get the last 9 bits. First of all, we have to move the 39th bit to the 0th index, and then we only get the last 9 bits. And this will directly be the index value for the table 0. For table 0, we do that operation and we get the index. And we make a table in that. So as I said, every index, first we calculate the index for the address, and then we have to store something, and the value can only be either be a block descriptor or a table descriptor. And the 0th index should never be a block descriptor, so we'll just create a table descriptor. Let's see how a table descriptor looks like. It's just going to take that physical base. Yeah. Is it physical? Yeah, it's physical base shifted to some value, and we set the bits that it is valid and it is a table. But I need to understand, I need to recall what does this do. Let's think. First of all, we AND it with FFFF. That means we are zeroing out everything that's in the last 3 nibbles, and we shift it by 12, we right shift it by 12, and then the entire value should be left shifted to 12. Why is that? Why the fuck? Let's just go to my article, because I fucking don't know. I guess it should be MMU part 1. I guess it's MMU part 2 then. Here we have the explanation. No, we still don't have the explanation. Maybe then it's MMU part 3. This is the proper explanation. As I said, so level 1 has 512 entries. There's just every entry will be pointing to some big GB. Leave that. We only have to care about I think let's go to the next 3 and 4th. Yeah, I guess this should explain even more better. So for 4 KB size, we have 47 to 39, that is 512 GB range. And then we have the 38 to 30 bits, that is 1 GB. With this we already explained everything. Now let's come down to the actual calculation. Yes. Let's take the input VA as 0x8000. And we should index 0 to 147 into the table. As I mentioned, if the VA bit is 48, then we can only index 0 to 47 bits, that is 48 bits. So for L0 table, first we have to find the index. How do we do that? We just right shift it 39 times, because we only care about it from the 39th bit. We right shift it. For the second table, we right shift it for 30 bits. Okay. What's the next calculation? I need the second calculation. What the fuck? That's all I have shown. What about how to make the table entry value? I didn't say anything about it. Okay, but at least I have given some articles. How do we set a value as table descriptor? That's the question. I think we can go to this article and we go to next. Updating translations. Holy fucking moly. Oh, fuck it. Translation grammar. Okay, this is the information I was looking for. Okay, but now I just want to understand how can I actually set a value to saying that it's a table descriptor or it is a block descriptor. I guess it should be here. Because I took everything from here. It must be here somewhere. Okay, PA base offset. Maybe I'm just missing some information that is directly in front of me. Yes, this is the information that we need. As I mentioned, the 0th level should always have a table descriptor, and then we can have a block descriptor. The page descriptor is just the final bits, that is the actual page. And how do we set it? So the value should be of a table descriptor. This is exactly what we have. We have to start from next. We have to store the next table address. If it's a table descriptor, we have to store the next table address, and we have to set the 0th bit to 1 1. That means it's a table descriptor. If you set it to 0 1, then it's a block descriptor. If you set it to 1 1, then it is page descriptor. And if you just set it to 0, then it's invalid. I guess that is what we do here, because valid descriptor means 0, table means 1, so it's 0 1 0 1. Why do I set? Okay, no, it's I'm right shifting 1 0 times. That means it's just the first bit is set to 1, and the second bit is also set to 1, so it's 1 1. And 1 1 means it's a table descriptor, and we just have to place the address here, and that's the location that I'm wondering, because as you can see, I am setting the table address here, but it needs to be from a certain bit. That's what I'm trying to see if it's mentioned anywhere, or how the fuck did I know that it should be from 12th bit, because that seems pretty odd. Also, this guy wrote really amazing article. Yes. I remember it now. I guess I have it in my blog too. Where did I show this? Because I remember showing something like that. It must be somewhere. Yes, it's here. No, it's for TLB. Let's go to third. It's not here. So I have. Maybe I just dreamed of it. Looks like did not show it anywhere. Let's go to fifth one. Okay, I did not show it anywhere. Okay. This is the actual. This is how the value should look like, and the output address should start from 47. 47 to 12 should be the actual address, and this is the valid bits. And there are some flags that we can set, but that's not really needed for the general use case. But these two values are important. That's how we say whether it is a table descriptor or is it a block descriptor. And the actual output address should start from 47th bit, and that's exactly why I have pushed it to 12, because our address starts from left to right. So if we have an address that is, let's say, 088888, we just right shift it to 12th bit, so it starts from the 12th bit to whatever bit it has actual value for. And why did I FFFF it? So that there is no top bits. So this is the base address. I'm just cleaning up the upper FFF bits, so there is nothing there. And okay, as you can see, I have knotted it. That's why it would be like 000 FFFFF. So everything else will be 1, and the top bits will be 0. And then I can just shift it, because we don't want to mess up the top bits, because top bits are not our part. We only have to update bits from 12 to 47, and that's why we remove the upper bits and then we shift it to 12. Interesting. Remove the upper bits, move the bits to right by 12 and then left by 12. Probably I should have written a comments down here, but yeah, it should work, because it did work, and I was using this blog mostly to understand how the fuck things work. Okay, so we know, if we have an address, we know how to calculate the index for the first table and add a table descriptor, and we just set the table entry that will be the index. For this index we set this table, that's it. And for the second, and as I mentioned, we have multiple levels. If we go to the next one, so far we have set it for the first table. We have to set it for the second table. In the second table we do the same thing. We calculate the index. How do we calculate index for L1? it will be almost the same. It's just that we start from 30th bit. For the first table, we start out from 39th bit. For the second table, we start from 30th bit. And for the third table, we start from 21st bit. And I did explain where did these values come from. It's just the VA bit. And based on the VA bit, we have these values. And then the second, for the L1 value, we are marking it as a table. And let's go to the third entry, and that will be the L2. For L2, we calculate the index and we mark it as a block descriptor. So this is a valid entry. So here, as soon as we reach this table, the MMU will know that whether a address is currently present here or not. Yep. I think I added this manually for some reason for this particular address. Calculate L2 index for this, and I just directly added the block descriptor and this. Okay, so now what do we do? What should our helper do? It's going to take a VA and it's going to map it to some PA. So should we add all the table entries, or should we only have to add the entry in the third table? So that's the question now I'm asking myself, because we have an entry in the table 1 for 512 GB. So definitely our input is going to fall under that. So I don't think we need to add anything in the first table. And for the second table, I think we have to add, because for the second table, from what I know, when I was debugging in the second table, I was only adding the index 2, because index 2 points to 0x800. But I will be using 0x1. That means I have to add a new entry in. So for every call to my helper function, I'll have to add two table entries. No, one table entry and one a block entry. A table entry in L1 and a block entry in L2. This is what I'll have to add. Okay. So what are the inputs I need? I need the kernel base address, and this is just the input. That's whatever virtual address that comes to me. I have to put it here. And then I need the L2 base physical address, because this is a table. I need this table physical address. Okay. So that's defined in the top, so that's also fine. I have that. And then I think I don't have to do anything else. I just have to call this, nothing much. Wait, table entry L1 table descriptor. And what's this? Why do I do it same thing for the physical kernel base address? What the fuck is happening? What the crap? We have the table entry. We calculate the index for a virtual base. We make a table entry with the physical base of the table, and we set entry within the table, within the L0 table. I'm setting index and descriptor value, and then I calculate the index for physical kernel base, and I make a table descriptor out of this physical base. Out of this physical base, L1 base physical, what the fuck? And then I add an entry to L0 base index 0 with this descriptor. Am I not just overwriting it? What the fuck is this code? Because I just added within this table, I have updated the 0th index to table descriptor as L1 base. I think this is all we need. Why the fuck did I write this? Maybe I'm just missing something, or maybe I forgot. That's why I have to fucking write comments. You fucking piece of shit. Virtual kernel base. I have. So, what does it mean to have an entry? So, whenever I try to, let's say, access 0x800, it's going to MMU unit, and MMU unit is going to look up that particular virtual address within the table and finally get the base physical address, because the third entry is going to actually store a physical kernel base, because this is the value. So I get this point. I just don't get why I have written it twice for every index. Am I fucking stupid? For this, we made a kernel block descriptor with this physical address, and we have stored it, because that is all we have to do. Even for this virtual address, I have calculated, this is the virtual address, I just calculated the index. Calculated the index, and This is the L2 index. I have made a block descriptor, and okay, how do I type for this chat? There's no type. See? I don't know how to type in my chat box. There's no option here. There's no option in OBS. So what's the kernel I'm developing? It's I don't know. There's no It's like probably a general purpose kernel, and it's just mostly self-learning based kernel. There's nothing. It's not going to be useful in any probable way, because I'm just doing this to understand most of the bits, because when I try to actually land this through just reading the source code of Linux, it just seemed too much. So if I could break things down in smaller pieces, I could understand it better. And I did understand a lot of stuff after trying to develop that here. And currently I'm trying to finish up my MMU unit, and I have it written down in my blog. Where's my fucking blog? Yeah, it's here. If we just go to here, yeah, I started off with the introduction. I guess I just built a kernel, and then the bootloader, and then interrupts, and then simple scheduler. And then we started off with MMU, and it's going like an endless journey. It hasn't been over yet. Okay, let's come back to our fucking... Where did we leave off? Okay, whatever. So now I have one doubt, because as you can see in this line, I have a virtual address, and I made a block descriptor that is, this is pointing to this address, and I just set that entry in the L2, and that is all we have to do, and it's the perfect way to do it. But I don't know why the fuck I have written it twice. I guess this should be enough. Why did I write this? I don't know. Maybe I was drunk. Virtual kernel base. I'm still trying to understand, because there's one difference here, because I have given it as virtual and physical. Maybe I'm mapping both the things. I'm mapping both virtual kernel base and physical kernel base. Okay. Oh, that's why. Because I want to create identity mapping. Now I understood. I need to create identity mapping. That is why I need to add entry for both the VA and the PA, because let's say if I try to access 0xFFFF000 some 80, this will be a virtual address. I need to add entry for this entry pointing to, let's say, 0x8000. This will be a physical address, and I also have to add a similar entry from the physical address, that's the actual physical address, to this. It will also again point to the same entry, that is 800. Why do I need this? This is because as soon as we enable MMU, we'll get a fault. Because the instruction right after the MMU enable will be pointing to a physical address, and we won't have a entry for it in our table. So it was just gonna fuck up the entire thing, and that's exactly why we have to add this physical entry at the beginning, and we are supposed to actually remove this. If not, it will be a security issue, because I guess I mentioned it somewhere. Let's go to 6th, not 6th. Let's go to 5th. Yeah, this is exactly. So this line is going to enable MMU. If I could. But the next instruction is stored in a physical address. But as soon as this is executed, we will be jumping into FFFF range, and to access anything we need a table entry, and we won't have a table entry for this, and it's just going to fault. And the moment we execute that, it's just going to fault. And that's exactly why we need to add two entries, one to map the physical, and then to map the one to map the virtual, and then to map the physical. And that's why I have added this. Ah, shit. Now I understood. See, adding the fucking comments would have been so much better. Now I had to completely revisit everything and understand it properly again, and I have to fucking waste my time in it. Why can't I write the fucking comments? I don't know. But yeah, but in general, our helper just has to do this one thing. It just has to take a virtual address, and it has to update it to a physical address and set the entry in the table. That is all we have to do. Maybe we have to do it in the L2 and L3. I don't think we need to do anything in L1. We just have to add no, we don't have to do anything in L1. We just have to do add. Oh, something is messed up. Okay, we just have to add a L1 entry. We don't have to add two entries. We want to add L1 entry and then L2 entry, and it should be good. So we could just copy fucking paste it. How do we copy paste it? Which? If we come here and yank, what is yank it? 3 lines. And if we go back to R, what the fuck is happening? Oh my god, I need that command. Okay, I hope my yank is still there. Where's my helper? Where's my helper? Where's my helper? It's here. I need to just paste it here. I need to add a L1 entry. I need to add a L1 entry, and I need to add an to add a L2 entry. Okay, that should be good. And we could take this here. It will be the VA. and the physical address is just going to be we just remove the top block. Maybe we'll write a simple helper for it. It would be fast if we write that. Do we have an helper? Something like that. Okay, I don't think we have it. So let's just write one. It's going to be a super simple operation. It's going to return a uint64 T value, and it's going to input it's going to get IPA identity and it's going to take a uint64 value VA, and what we have to do is we have to add FFFs in the top. That is all we have to do. So we can just do it like 0x FFF FFFF 1 2 3 4 1 2 3 4 1 2 3 4. Okay, I hope I added proper force. 1 4 4. I didn't add it properly because now I'm again confused. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. Okay, now we can just and it or r it with our VA. That's it. This should give us the this does not look like a helper. We could just write it as a define then. Define PA. How do we take an argument for macro? Macro. I haven't written any macros with arguments. What the fuck? I think it's just the same thing. We just take VA and we return PA. We don't return PA. We just return this, and we add. I think that should be correct, and I guess I have to also put a bracket around this. Okay, I hope this is correct. Let's delete this and go to the top and add it here somewhere, and so it should be fairly simple. And we don't need a function for it, it's just too much overhead. We just need a macro. And it would be PA to VA, that is what did we get? PA identity. Okay, and it would be a VA. What the fuck? What do you mean unexpected expression? Okay, it's just going to copy paste it. Okay, then I don't need this thing. No, it should work. Yeah. Sometimes I just forget things because they are compile time, and this is in runtime, so macros are compile time, so we don't need that fucking thing. Where's my helper? Where's my helper? Where the fuck is it? Okay, it's here. Now we can calculate the index for L1 for this VA. We make a table descriptor for this PA. No, wait. We make a table descriptor for the L2 table. We have to actually add this in. We delete this. Okay, it's correct. Wait, I'm wondering. This is L1 physical table. Within that table, in index 1, I have to add a descriptor. And that is this. I think it's correct. Okay. It looks correct. At least it feels correct. Now we can take this one. Yeah, we'll take this one because it has everything already. And if we go back to our part and if we paste it, and then we could take L2 index will be the VA, and the physical would be, I guess we can just uint 6014 PA equal to and add PA here and add PA here, and I think we are good to go. Yes, we added an entry in the L1 table for this VA to this PA, and we added the L2 entry for this VA with this PA, and that is all there is to do. We can just return true. Yep. Is there anything else I'm missing? Yeah, I have to also consider the total. So if the total is if there's only one page, then it makes sense to just add one entry. But it is possible that there are multiple pages that are allocated, so we need to loop this somehow. Also make sure the VA is added by 496 for every total entry. Yeah, let's do that. So it should be like for int 64 t I equals 0, I less than total I plus I. Okay, now we are getting somewhere, and we could delete this. Oh fuck me. I'm in which mode? I need to be in visual mode, and I can paste it and okay. Okay, for every entry we need to do that, but we also have to update VA. Let's just take current UN64 current VA equals to VA plus 4096 into I. That's it. Because if it's zeroth index, then we won't add anything. If it's the first index, we'll add 496. If it's the second index, we'll add 496 into 2, and I think it should work. Now we just have to update these values, current VA and current VA, and PA will be same. For this current VA, we have the same PA, and we have the same PA. Yep, and we can return true. We could do some sort of error handling and return false if something goes wrong, but I guess that's for another day. It's been 1 hour, but I have to I think that is all there is. We have a virtual address that starts somewhere, and we know the page size is 496, so we can multiply it to get the current VA, and then we can use that to do whatever we want to do. And we know it's the total, and we only have to do till the total, and we add the entries and we return true. I think everything is good. Yes. It should be good. Now it's time to fucking try this out. Where's my gaming? But I have to take a piss. Fucking. Oh, shit. Oh, there's no way to stop the stream. Fuck me. Okay, guys, but I guess I'll try it later. But yeah, but it should be done. But we have, let's just recap it once more, what we have done, and I'll end the stream for today. So as you can see, yesterday we tried to use, because we know that we have allocated some pages using our initial helper, and we know the total number of pages that are allocated, and we know the index within the table. Based on the index, we can find the physical address. Now we have to use that physical address to map the page table entries, because for every virtual address that we try to access, we need a physical page table entry. And if, let's say, we were allocated with some physical pages, we need to find the respective virtual page initial values, and then we need to add them to the mapped entry. And if you check how the mapped entries works, we just have to add a level 1 entry and level 2 entry, and we have helpers for it, and everything is already defined during the initial MMU stages. So we just use those helpers directly, and we calculate the index within the table, and we set it to table descriptor, and we set the table entry. And for the second entry, we calculate the index, we mark it as a block descriptor, and we set the entry. And we do this for all the total, for the total entries. So the total entries will be calculated by page size into I. So I guess we need to define this somewhere so that it will be configurable if I change the page table size, I guess. Yep. Yeah, that should be good. Okay, guys, thank you. We'll see you probably maybe today or next week. Probably I'll be streaming. Yeah. Let's see. Thank you guys. Bye.